Okay, so what we want to do in this session is we want to focus on, there are just a couple of different kinds of calculations that we can do that are related to unit cells. And so what I want to do is I want to focus and highlight on kind of the three most common ones. And then I'll give you a chance to practice a couple of them on your own. And so if you're looking at, what am I going to see on the quiz on Wednesday about this? It's primarily going to be these kinds of calculations. Can I calculate density given information about the unit cell and its composition? Can I calculate the diameter or the radius of an atom based upon its density and some other information? And then the other piece of that quiz on Wednesday is going to focus on semiconductors, and we'll talk about that tomorrow. And tomorrow is going to be calculation free, basically. Concept kind of ideas, looking at some specific examples of lattices and crystal structures and how some of those physical properties are impacted, but nothing calculation really oriented at all. This is the calculation day. Tomorrow's the concept day, and we'll close it off. So here's our first question. At 1057 Celsius, the unit cell for iron metal is face-centered cubic with an edge length of 361 picometers. What is the atomic radius of iron at this temperature? Okay, so this one is relatively straightforward. And the reason it's relatively straightforward is because they are asking us for things that we have equations for directly. We don't have to do any conversions first. We're told that it is face-centered cubic. And since it is face-centered cubic, we know, we can look at the equation sheet, that the radius of that iron atom is going to be equal to the square root of 2 over 4 times the edge length. So this one's real simple. We've got the edge length, 361 picometers. We just have to apply this adjustment to it. Radius is equal to the square root of 2 divided by 4 times 361 picometers. If I do the calculation, 361 times the square root of 2 divided by 4 to 3 significant figures is 128 picometers. Okay, so sometimes these calculations are really just this simple. We identify the type of unit cell, we find the equation that relates the edge length and the radius, and we just plug and chug to get to the answer that we are ultimately looking for. All right, any questions with this? All right, let's take a look at another example. Here's an example of a more common kind of question, because let's be honest, most of the questions that we get in smart work, the ones that we get on our quizzes, they don't tend to be that straightforward. So let's take a look at something that's a little less straightforward, but still utilizes the same kinds of calculations. Copper crystallizes in a face-centered unit cell with an edge length of 361.49 picometers. What is the density of copper? Now, you might be looking at this and go, oh, whoa, wait a second. where do I possibly get density out of this information? I can find the radius, but what good is that to me? Well, here's where we have to kind of break down what it is that we need. To find the density of copper, we're going to need the mass of copper and the volume of copper. Now, for the mass, presumably we're going to use grams. For the volume, we're going to use cubic centimeters, because most of the time density is given to us in grams per milliliter. Remember that milliliters and cubic centimeters are the same thing. And so when we talk about the density of a solid object, we usually use grams per cubic centimeter, just because if it's a solid object, we can measure it with like a ruler or something like that, a caliper, something. And so the measurement's usually some sort of distance cubed. In this case, centimeters is kind of the preferred way to go. So from that standpoint, doesn't seem like we still have all that much information at our hands. But there are some things that we can pull out of this that will help. So for example, being that it is face-centered cubic, there's two things that we know. First of all, we know that there's a relationship between the radius and the edge length. And so that could help us a little bit, although if we're dealing with a cube, we already know the edge length of the cube, well, isn't volume length times width times height. And if it's a cube, all those dimensions are the same. Kind of have that already, right? So if we were given the radius of the copper atom, we could use that formula to figure out the edge length. But for the volume, 361.49 picometers cubed, we could easily find that. Might be in our better interest, though, to turn that into centimeters first. Because if you remember from chapter 1, converting units of volume to each other can be kind of a tricky enterprise, because you got to take the conversion and cube it to do it. Might be easier for us to first take this 361.49 picometers and convert it to centimeters first. Now the conversion, we know that there are 10 to the 12th picometers in 1 meter, and that in every meter there are 100 centimeters. So 361.49 times 100 divided by 10 to the 12th, we get 3.6149 times 10 to the negative 8th centimeters. So if I'm trying to find the volume would be 3.6149. And yes, all of those significant figures are still significant, times 10 to the negative 8th centimeters. That is the edge length in centimeters. So if we cube that, we would get to 5 significant figures, 4.7238 times 10 to the negative 23rd cubic centimeters. Okay, so there's our volume. Sounds kind of small, but again, we're talking about a single unit cell. So we're talking on very much the atomic scale. It's going to be small. Now, what do we do about the mass? Well, here's where our idea of face-centered cubic can come in again. We know that we have in a face-centered cubic cell 4 atoms per unit cell. So really what we need to figure out is what is the mass of 4 atoms in grams. And for this, we're going to need a calculation that you thought you had put behind in Chem 105. Conversions at the atomic scale. So 4 atoms of copper. There are Avogadro's number of atoms in 1 mole of copper. And each mole of copper weighs 63.55 grams. So 4 times 63.55 divided by Avogadro's number to 4 significant figures, 4.221 times 10 to the negative 22nd grams. So density is equal to the mass of the copper, 4.221 times 10 to the negative 22nd grams divided by 4.7238 times 10 to the negative 23rd cubic centimeters. Which would give us a density of 8.936 grams per cubic centimeter, which is actually pretty close to what we think of as the density of copper at room temperature. So depending on your resource, we get 8.94, 8.95. So we're not far off. So this is an example, like I said, of probably a little bit more common of conversion for this kind of problem, where we need to use our definitions to solve something attainable, but not direct. So the first calculation was very direct. I got the edge length, it gives me the radius. I get the radius, it gives me the edge length. Here, I have to interpret what the unit cell is and kind of take it from there. All right, any questions about this example? All right, same kind of question. Here I have a body-centered cubic unit cell for iron in the form of ferrite. And it has an edge length of 287 picometers. So we're going to do the same kind of calculations here, We know that the volume is equal to the edge length cubed. We're just going to want to convert this 287 picometers into centimeters before we do the cubing. So 2.87 times 10 to the negative 8th centimeters is the edge length. So volume would be 2.87 times 10 to the negative 8th centimeters. We're going to cube that to get cubic centimeters, which would give us 2.36 times 10 to the negative 23rd cubic centimeters. So there's our volume. Now to find the mass, this time we have to recognize that we're talking about a body-centered cubic. So this one only has 2 atoms per unit cell, not 4. So our conversion is going to start with 2 atoms of iron. There are Avogadro's number of atoms in 1 mole of iron. And the molar mass of iron is 55.85 grams. So the 4 significant figures, and again, if you're having trouble following the sig figs here, the 2 is an exact count. So it doesn't factor in. The number of sig figs that I carry in this calculation of mass is based on how many I carry in the molar mass. So whatever number I round that to, that's going to be how many sig figs come out of this calculation. Because this number is exact, this number is exact. So we're running it off of here. So 2 times 55.85 divided by Avogadro's number is 1.855 times 10 to the negative 22nd grams of iron. So our density is going to be that 1.855 times 10 to the negative 22nd grams divided by the volume 2.36 times 10 to the negative 23rd cubic centimeters. Three significant figures, 7.86 grams per cubic centimeter for iron here. So if you were curious, how do we come up with those values of densities for these different substances? This is largely how. It's not somebody in a laboratory, doing a whole bunch of stuff by displacement. It's largely based on the crystallography. What is the edge length? Is it a pure substance? Those kinds of things. We can get a lot more accurate results that way than by doing it the way that we've done it in lab, where you measure out a little bit of water and drop the cylinder in and see what happens. All right, any questions with this example? All right, I want you to try one on your own here then. We've got krypton crystallizing with a face-centered cubic unit cell, edge length of 559 picometers. What is the atomic radius of krypton? So take a minute, go ahead and go through this, and we'll come back and see how you did. All right, let's see how we did. So this one should have been a relatively straightforward kind of application. We're talking about a face-centered cubic cell, and we know its edge length, so this is our value of L. It's asking us for the atomic radius R. So R in a face-centered cubic is equal to the square root of 2 divided by 4 times the edge length. So just plugging in the values that we have, we should get a radius 559 times the square root of 2 divided by 4 to 3 significant figures, 198 picometers should be what we're getting as our answer. Any questions with that one? Yeah. Not for this kind of a question, just because, you know, whatever you put in as the unit for the radius or for the edge length for that matter will come out on the other end as the same unit. So the only reason that you would be doing something like that is either because the problem asks you, what is the atomic radius in meters? And so you take that number and you divide it by 10 to the 12th, and you get 1.98 times 10 to the negative 10th. Or for some reason, you need to do something like one of the problems that we did before with the density, where turning that edge length, let's say that we started with radius and we needed to figure out the edge length to figure out the volume. Well, in that case, yes, it would make sense, convert it to centimeters first, use the centimeters to convert to the next thing so that you had the edge length in centimeters when you did the volume calculation. But aside from one of those two reasons, no, there's no reason to do the conversion. Keeping it in picometers is going to keep the numbers nice and round, and not in scientific notation, which, as we know, scientific notation's there to give us an idea of scale, but it's not always easy to understand the quantity if it's got a big negative or a big positive exponent attached to it. So really, only if the question asks you to do that would you do it, unless you're using the result of that calculation to do some other calculation that was going to require a conversion. All right, other questions from this problem? All right. Determine the density of nickel if it has a simple cubic unit cell and an edge length of 0.3524 nanometers. So slightly different focus on the And just in case you need a reminder, nanometers are on the billion scale, not the trillion scale. So 10 to the negative ninth meters in a nanometer, or 1 billion nanometers in a meter, however you want to look at that. So same thing, go through the calculation here, see if you can come up with an answer that makes sense, and we'll talk about it in a couple minutes. All right, let's see how we did, and then we can close this up for today. So the things that we have to take advantage of, this is a simple cubic, so that we know that there's going to be one atom per unit cell. And our edge length of 300 of 0.3524 nanometers. This is where we could have got tripped up if we were looking at the previous examples, because they were all in picometers. And so we have to do that conversion properly. So 0.3524 nanometers. Every meter has 10 to the 9th nanometers in it. And every meter has 100 centimeters in it. Some of you combine these two steps together, that's perfectly fine. If you know what you're doing, you can take shortcuts. So 0.3524 times 100 divided by 1 billion would give us 3.524 times 10 to the negative 8th centimeters. So volume would be the edge length cubed. So 3.524 times 10 to the negative 8th centimeters, quantity cubed. Which would be the four significant figures, 4.376 times 10 to the negative 23rd cubic centimeters. And then for the mass, we're starting with one atom of nickel. There are Avogadro's number of nickel atoms. In 1 mole, and every mole has within it 58.69. So 58.69 divided by Avogadro's number to 4 sig figs again, 9.746 times 10 to the negative 23rd grams. So our density would be the mass, 9.746 times 10 to the negative 23rd grams over 4.376 times 10 to the negative 23rd cubic centimeters. To 4 significant figures, 2.227 grams per cubic centimeter. All right, now, before we break off here, just understand you can be asked to go the other way. you could be asked to go the other way, where you have to take one of these pieces of information and figure out the other. So what I mean by that is, let's say that we were given the density of the substance and its edge length. You could work backwards to figure out the number of atoms in the cubic cell to figure out what kind of cell it is. Simple, body-centered, or face-centered. You could be given that information about the unit cell and have to work backwards to figure out the edge length or the atomic radius. So there are other spokes, there are other directions that we can go, and your homework for this section will likely explore some of those. So if you do have any questions about those as they come up, if you're unsure of how to make the algebra work, send me a note about those things, and we'll work through them before we get to the quiz over this material on Wednesday morning. But this concludes the calculation half of chapter 18. So this assignment in Smart Work is not actually going to be due tonight. It's going to be due tomorrow night. And the primary reason is there's a lot due in these next couple of days. I'm giving you some flexibility. I want to make sure that you have time to study for tomorrow's exam. So however you figure to kind of manage that time over the next 48 hours, I'm going to let you do it in whatever way seems best for you. Do understand there is not an end of chapter assignment. There is no bonus assignment for chapter 18. And the primary reason for that is we are only covering very selected sections of that chapter. So rather than making that whole thing kind of work for us, what we're going to do as far as the bonus is concerned is basically, I'm gonna take whatever the value is, and in Blackboard, it's going to be half of that. So if you're looking at the assignment and it says it's a 25-point assignment, it's going to actually be a 13-point assignment. So work as much as is necessary to understand the topic. If you want to go for the extra bonus points, complete the assignment, absolutely work through it that way. Otherwise, do enough to get yourself full credit. And if you understand it and you got other things that you got to move on to, because, there are 13 assignments due for the lab this week, work on those things. Perfectly okay. It's why I designed it that way. Any questions before we take off for the day, or at least for now? All right, get your last participation point before you leave, and then I will see you. Can we do 1:15? Is that enough time for everybody? Okay. You can build them as you go. There's no pre-lab assignment for it.